Welcome back. So in this lesson we are going to learn a very important topic, which is pruning. Okay, this topic is very important in decision trees. So first we need to understand how to avoid overfitting, and we discussed what is overfitting before. The first way to avoid overfitting is to acquire more training data, right? Because the more data you give it to the model, the less the chance that you will get overfitting, right? So give it more training data, the chance for overfitting will decrease. But most probably you don't really have this option, right? You cannot really collect any more data. This is the data that you have available at this moment, and there is a good chance that this is the data that you can collect anyway, right? So if we wait for another month or two, you cannot really collect any new data. So this option is most probably infeasible, right? The second option is to remove irrelevant attributes, and this is from the pre-processing. So in the project you will see that we are doing this step to avoid overfitting and to increase the efficiency and accuracy, is by removing the irrelevant attributes, and we do this by pre-processing and visualizing the data, understanding what are the problems and so on. The third option to avoid overfitting is by growing the full tree, so we don't really have maximum depth, so we build the full tree and after that we prune the tree. So it's called post-pruning. Okay. The fourth option to avoid overfitting in decision trees is by ensample learning. We don't really know yet what is ensample learning, and we will leave this to the next section. In this next section, we are going to learn everything about ensample learning. Okay. So we are now focusing on the option number 3 to avoid overfitting, which is growing the full tree and then post-pruning the tree. So what is pruning? We can perform pruning either before building the tree. Okay, this is called pre-pruning, and this is actually what we have done when we had the maximum depth, right? Or we can prune after building the tree, which is called post-pruning. Okay, and we have already performed pre-pruning, as I said, by specifying the maximum depth in our implementation or by controlling the different hyperparameters in sklearn implementation, such as the minimum sample splits, the maximum leaf nodes, and so on, right? However, this approach is not preferred, and it shouldn't really be used alone, because a seemingly worthless split early on in the tree might be followed by a very good split. So let's say we reach the depth of 4, right? And now we won't really go any deeper, but if we went deeper, so we can split right now, but this split is not actually adding any information. But after we do this split, we might get a very good split from there, right? So we don't really want to pre-prune the tree. We want to post-prune the tree, okay? So we should combine pre-pruning with post-pruning, or have post-pruning alone, okay? The post-pruning is also known as cost complexity pruning, and it's also known as weakest link pruning. And we will understand now why it's called cost complexity and why it's called weakest link. Now, how we can perform the post-pruning? We perform it in a bottom-up manner. The idea is very basic. We start at the leaves, right? We build the full tree, so we will start from the leaves, and each node is replaced with its most popular class. So we will go to the leaves of the tree, and we will replace each node by its most popular class. Okay, if the prediction accuracy is not affected, then the change is kept. Okay, we can also explain it another way. Now, rather than considering every possible subtree, we consider a sequence of trees indexed by a non-negative tuning parameter called alpha, and this is the alpha we saw in the sklearn. Okay, so for each value of alpha, there corresponds a subtree like this, right? So this is a hyperparameter. Alpha is a hyperparameter. So it can be 0, it can be 0.1, it can be 0.2, 0.3, and so on. And for each value of alpha, there corresponds a subtree such that the cost here is as small as possible. So what is the cost? The cost is basically the error of this tree. So we build the full tree, and then we have another error coming from pruning the tree, right? So if alpha is equal to 0, then the error of the tree will be basically the same. But if we have a value for alpha, right, if we have alpha 0.1 or 0.2 or 0.3, then the error will increase, right? So you can think of alpha as a regularizer, okay? So T absolute, right, indicates the number of terminal nodes of the tree T, right? So how many terminal nodes we have at this tree? So at the very beginning, we have all the terminal nodes. Let's say that we have n terminal nodes, and let's say that n is equal to 10, for example, okay? Now, after we perform the pruning, we will have 8 or 7 or 5 or 3 or whatever, right? We will have a new number of leaves. And the tuning parameter alpha controls a trade-off between the subtree's complexity and it's fed to the training data. So basically, when alpha is equal to 0, then the subtree, the new subtree, will simply equal T0, right? So T0, the tree without removing anything from it, right? Now, if we increase alpha, then branches will start to be pruned from the tree, okay? So again, if we explain it from a bottom-up approach, we start from the leaves and we remove the leaves, and instead of having the leaves, we have now a representation of these leaves, right? For each node, we replace it by its most popular class. And we can explain it also in another way using the hyperparameter called alpha. So if alpha is 0, then the tree, the new tree, is basically the original tree. And when we have alpha equal 0.1 or 0.2 or whatever, then we are controlling the subtree's complexities. So this T is the subtree, right? And this absolute T is the terminal nodes of the new tree, okay? So if alpha is large, then this means we are giving a big penalty for the terminal nodes. So this means more and more branches will start to be pruned, okay? Now, to understand better all this, let's go to the code and start seeing graphs and understand better all this conceptually, okay? So inside the classifier, inside the sklearn classifier, we have a function called cost complexity pruning path, right? So let's read the description for this function. It's saying compute the pruning path during minimal cost complexity pruning. See minimal cost complexity pruning for details on the pruning process. So let's go to the documentation for this function on sklearn. So here we are. It's saying post pruning decision tree with cost complexity pruning. Okay. Decision tree classifier provide parameters such as and so on, so and so. So let's read this. Total impurities of leaves, okay, versus effective alphas of pruned tree. The minimal cost complexity pruning recursively finds the node with the weakest link, right? So that's why we call it the weakest link. So what happens is that we build the full tree, and after we build the full tree, we will go and find the weakest link or the weakest node. So what is the weakest node? The node that if we remove it, then the total error or the total accuracy will not be affected that much, right? So we have the full tree, and then we have the subtree or the new tree without this node, right? How we can decide this node? By using the alpha, right? So we characterize this weakest link by an effective alpha, where the nodes with the smallest effective alphas are pruned first. So if we have a node that has a very, very small alpha, then this means that this node will be removed, right? Or it will be pruned, okay? So to get an idea of what values of CCP should be used, sklearn provide decision tree classifier cost complexity pruning path. This is the function that we were trying to use that returns the effective alphas and the corresponding leaf impurities at each step of the pruning process. So as alpha increase, more of the tree is pruned. So if alpha is very, very small, then this means we are not really pruning any nodes whatsoever, right? But if we increase alpha, then this means we are trying to prune more and more of the tree. Because if we increase alpha, then this means the probability of this link to be weak is higher. So the probability of removing this link or removing this node will be higher and higher. And this will in fact increase the total impurity of the leaves. And this is the opposite of increasing the information gain, right? So increasing the impurity is similar to decreasing the information gain. So this is not something we really want, right? So let's go back to the code. We have here our decision tree. The criterion is Gini, right? And the maximum depth is 7, right? We fed the decision tree, and after that we have here the cost complexity pruning path. This should return the path, right? And we have inside the path the alphas, right? So all the alphas values and the impurities associated with the alphas, right? So we have for each alpha a specific impurity. Now let's plot the effective impurity with the total number of leaves, or the total impurity of these leaves, right? So if we run this, you will see that we have an effective alpha from 0 to 0.03. And when we increase the effective alpha, then the total impurity increases, right? So you can look at the total impurity as the added error, right? So here we have a total impurity of nearly 0.018, right? And when we increase the alpha, the total impurity increases exponentially, right? So if we increase from 0 to 0.03, you see that the total impurity increases from 0.2 to nearly 0.28, right? Or 0.29, right? So this is a huge increase. So we need to train a decision tree using the effective alphas. So the last value in the alphas is actually the alpha value that prunes the whole tree, right? So we don't really want this, because if we do so, then we don't really have any tree. We have only one node. So we will fit all the trees using all the alphas other than the last alpha. So we will loop over all the alphas, right? And we will go to the decision tree, build a decision tree with this specific alpha, and we will fit our classifier using this alpha, okay? And then we will have this classifier appended to the list of classifiers. And after that, we will print number of nodes in the last tree is with CCB value equal to this one, right? So if we do so, you will see that we have number of nodes in the last tree is 3, right? So this is the tree before the last tree, right? We have 3 nodes and the CCB value is 0.07. So this is the last tree. Now let's take a look at the node counts and the depth, right? So if we print the number of nodes versus alpha, right? So when we increase alpha from 0 to 0.0001 even, right? The number of nodes decreases from more than 10,000 nodes, right? So this is a huge number of nodes to nearly 0, right? So nearly 3, 5, 10. We cannot really see it on this graph because the scale is very, very large. It's from 0 to 10,000, right? But as you can see, when we increase the alpha, very, very small increase, then the number of nodes decrease sharply, right? And the same for the depth, right? When we increase alpha, the depth of tree decreases from more than 50 to nearly 10 or less, right? So when we increase alpha, a very, very small increase, the depth decreases sharply also, right? So if we check this value, or if we stick with this value for alpha, right? Let's say 0.001, right? And go back here, you will see that when we increase alpha from 0 to 0.001, then the impurity increases, but not that much, right? So this is actually a very good value for alpha. So this value will prune nearly the full tree, and at the same time, the added error is not that much, right? So let's also print the alpha with the accuracy, right? So let's plot here. The training accuracy is in blue and the test accuracy is in orange, right? So as you can see here, this is the accuracy for the training set, and we have here alpha. So the training accuracy at the very beginning when alpha is 0 is nearly 0.97, right? So we have 97% accuracy or more. But at the same time, the testing accuracy is nearly 80%, right? Or 82%. So this is a clear sign of overfitting, right? But when we increase alpha to 0.001 even, right, the training accuracy decreases, right? But at the same time, the test accuracy increases, right? So this is the best spot. This is the sweet spot. Because here we have the training accuracy very near to the test accuracy. So the test accuracy, this is the highest test accuracy we can get. And we got it after increasing alpha. So increasing alpha led to a decreased number of leaves, a shallower tree. So that's why we avoided overfitting by using alpha, right? So if we check the CCP alphas, you will see that when alpha is set to 0 and keeping the other default parameters for the decision tree classifier, the tree clearly overfits, right? Leading to a 97% training accuracy and an 82% testing accuracy. But as the alpha increases, more of the tree is pruned, right? So we are creating a decision tree that generalizes better. So if we set the alpha to be 6.2 times 10 power 4, then this maximizes the testing accuracy, okay? And you can check it from here, or I think it's even changed after so many iterations, but basically you can take a look at what is the value here for the alpha that led to the highest testing accuracy. Okay, so this is the concept of post-pruning, or the concept of the alpha hyperparameter. So this was a complex lesson, I know, but it's very important to understand the idea of pruning even if you don't really understand the mathematics behind it, right? So the next lesson will be optional, and we will talk about the gain ratio. So this is an extra or an optional lesson, but the lesson after that, which is the pros and cons of decision tree, is very, very important. So let's go now to the gain ratio.